In today's lab, we are going to be calculating the mass of a black hole by observing the motion of a star orbiting the black hole and applying what we know about forces. To do so, we will create a program on VIDLE that will consider the parallel and perpendicular forces to find the net force. From there, we will rearrange Newton's law of gravitation and substitute known values to compute the mass. Unlike the first two labs in which we plotted the predicted motion given the net force and initial conditions, we are now going to try and determine these initial conditions and the net force based on observations of the motion. Based on these observations, I determined that the mass of the black hole to be 1.9899 10 to the 31st kilograms, and here's how that mass was determined. We will begin by identifying the system whose motion we're studying and, using the observation of the system's motions, find the total forces. From there, we will specify the interactions and solve for the unknown, which is, in this case, the mass of the black hole. Here is a diagram roughly depicting the net forces on the star at a particular position while it is orbiting the black hole. Just as a note, I will be noting each variable as I will have labeled it on VIDLE such that you can more easily connect the program with the physics concepts in the motion diagram. In this lab, the system is the star orbiting the black hole, and the only forces acting on the star that we are considering is the force acting in the parallel and perpendicular direction. Newton's second law tells us that changes in speed are caused by the non-zero net forces acting in the parallel component, and changes in direction such as curving are caused by the non-zero net forces acting in the perpendicular component. Now the last thing we should consider before moving to our program are useful equations to note: the net force and momentum in the perpendicular direction. The other major equation we need to consider before moving is Newton's fundamental law of gravitation, which can be manipulated to solve for the mass of the black hole, denoted as m2. Now we have everything we need, we can create our program. In the program, the mass of the star, the initial position of the star, and the time step are all given to us as the initial conditions. And if we move on, an index is created using a while loop to facilitate the time steps. Now onto the calculation loop, where we can apply the physics concepts. In the beginning, we define the initial and final velocities, and then move forward to calculate the change in velocity. Thus, the change in momentum, by multiplying this change in velocity by the mass of the star. The change in momentum can be denoted as dp dt, which equals to the change of momentum over the change of time. And this quantity is equal to the net force. In this while loop, we can break up the parallel and perpendicular components that constitute the net force. We know that dp dt parallel is equal to the change in the magnitude of the momentum multiplied by p hat. Thus, in order to solve for dp dt parallel, noted as dp dt par, we need to solve for p hat and the magnitude of dp dt parallel. By manipulating this equation, we can calculate that p hat is equal to the vector of the momentum divided by the magnitude of the momentum. Similarly, the magnitude is noted as the change in the momentum divided by the time step. Together, these two variables help to solve for the net force dp dt in the parallel direction. Next, we solve for the perpendicular component of F net, noted as dp dp perpendicular. In order to do so, we utilize the fact that we know that F net parallel and F net perpendicular are the two components that constitute F net. It can be written as F net parallel plus F net perpendicular equals F net. Thus, the equation can be rewritten to solve for F net perpendicular as F net minus F net parallel, which we see is actually written here, dp dt minus dp dt parallel. That's basically F net minus F net parallel. Now that we have the parallel and perpendicular components of the momentum, we can move on to the last major adjustment, which is essentially to rearrange Newton's fundamental law of gravitation in the program, which we have already done in the PowerPoint, so we put it just in the program, so solving for the mass of the black hole. Lastly, we request the program to print the mass of the black hole after the model is run, which we do here. Okay, we will now run the program. Okay, so this is the result of the program after it's been run. The black hole represents the net force in the parallel direction, the blue arrow represents the net force in the perpendicular direction, and the yellow arrow represents the resulting net force. And the mass, as we can note, is 1.989 times 10 to the 31st. Okay, now on to the discussion questions. We know that F net is equal to dp dt, which also means the parallel and perpendicular components of F net are also equal to the parallel and perpendicular components of the momentum. Essentially, F net, this force, is what causes the momentum. And so although these two quantities might be the same, they must be interpreted differently. It's more like a cause-effect relationship. The force causes a change in momentum. And momentum is something that can be calculated using position data and mass data. It's also visible. And thus we can use this relationship to help understand the force. But essentially we need to understand that these two quantities, although they might be the same, must be interpreted differently. So the net force causes the change in momentum. Now on to the what-ifs question. So is it possible for you to find the value of the mass of the new black hole that is different from the mass you found for the original one? So looking back at Newton's fundamental law of gravitation, we can observe that if the motion of these stars is the same, then that means the position of the star is the same. That said, if the motion and thus the position of the object is the same, then the net force acting on the object must be the same. Given that the net force must also be the same, the value of the mass of the star multiplied the new mass of the black hole must be equal to the mass of the star multiplied the mass of the old black hole. If the black hole's mass is different, then the star's mass must also be different to account for the change. Everything considered, you cannot change the mass of the black hole and still have the same motion because the inward force will be stronger in accordance with Newton's fundamental law of gravitation, and thus will pull the star closer to the black hole. Okay, and this concludes the lab for today. In this lab, we saw how we could extract information about the mass of the black hole simply by observing the motion of the star orbiting the object. Conclusively, hopefully you gained a clear understanding as to how we can use these observations of motion to identify the object's net force and initial conditions, such as the mass.